We had those two sets, pi, say, the upper, the lower, and convex of those pi of d, the smaller, the upper, bigger, with these inequalities. And basically what we did now, we proved this, right? Because we constructed pure resolution for every d, and so it kind of means we kind of constructed something at every corner of the set, and then we know by the direct sum construction that the set is convex, so we get everything inside this normalized Betti table. But now we want to show that there's nothing inside, outside of the cone, right? And this is a construction of Eisenbach and Schreier, and not only that they proved it, but they also realized that it has to do with another cone, okay, and of completely things that seem to be non-related. So let's first talk about cone of cohomology tables. So we start with E to be a vector bundle on Pn minus 1. And really, you see, I think of this as being the projective space on the same vector space E that we had n variables. Okay, so what is a cohomology table? Cohomology table of E will be now gamma of E is another infinite thing, but going now horizontally. So here it will have rows from I equals 0 to I equals n minus 1, and columns which are from the integers j, and the gamma ije is just dimension of hi Pn minus 1 E twisted by j. Okay, one has to be just careful that Eisenbach and Schreier write those tables like this. Okay, but doesn't matter. Okay, so again, one could ask the same question as for resolutions. Well, what are the possible cohomology tables of the vector bundles? Again, I could normalize. Again, notice that, say, the set of normalized gamma of E, we could normalize, I don't know, taking that the sum in that column has to be 1. Normalized gamma is again convex. So again, we have a cone, okay? And we might ask now, what are the extremal rays in that cone? And well, Eisenbach and Schreier found out the answer to that question. So let's define the corresponding notion. I should point out also that the bundle E has a Hilbert polynomial. Namely, there exists D such that for every D0 maybe, D bigger or equals, well, maybe let me just write H E of D is the Euler characteristic of ED. Right? So that's a Hilbert polynomial, and H of E is a polynomial of degree n minus 1. And so we say that a vector bundle E has a supernatural cohomology if two conditions are satisfied. First, for every j, there exists at most one I such that hi Pn minus 1 E of j is non-zero. And second, H of E has n minus 1 distinct integral roots. The name supernatural comes from the fact that this bundle satisfying condition 1 were already called the bundles with natural cohomology. Okay, so that's what came up. And it turns out that, and Eisenbach and Schreier proves that, among other things, is that this is an exactly analogous picture to the picture of Betti tables. Namely, the bundles with supernatural cohomology form extremal array in, okay, so one theorem that they prove, bundles with supernatural cohomology form extremal arrays in the cone of cohomology tables. Then, second, there is a simplicial structure analogous to what was happening for Betti tables. Namely, again, you see, if I would like, remember, for Betti tables, I was taking this set pi, d lower, d upper. Okay? So if I would want to do it for bundles with cohomology tables of the bundles, I would fix the roots, the lower, the upper, and I would consider only bundles such that the Hilbert polynomial would have the roots in between, okay, component-wise. And then, again, the maximal chains would give me the simplices, okay? So the simplices, maximal chains of integral root sequences. Okay, so, but again, you see, one can define this, but we don't even know that the bundle with supernatural cohomology exists, okay? But in fact, one can find, again, just like for pure resolutions, one can find a family of vector bundles with the supernatural homology and the arbitrary roots, okay, coming from representation theory. Yeah, I should make one, remark. I'm giving here the kind of the characteristic zero picture, like for pure resolutions that I constructed, work only in characteristic zero. The bundles I construct work only in characteristic zero, but they are much nicer. The constructions then can be modified to also give something characteristic P, but it's not as straightforward. So in characteristic zero, why those supernatural bundles exist? Okay, this has something to do with something called the Bott theorem. So let me just, and from this I'll show you that they exist, and they have to do with Schur functors. Namely, so existence of supernatural bundles, well, I mean by this with arbitrary sequences of roots, well, so you see, On POV, I have this line bundle, which is, well, sometimes it's denoted by tautological subbundle or of -1. So this is a set of pairs X POV for XL in E cross P of E such that X is in L, right? Every point in P of E is a line in E, and then I take this set of pairs. This is a line bundle, tautological subbundle, and then I have the sequence of bundles over P of E. And this is called the tautological quotient bundle. So the fiber over a given line is just E divided by that line. So this tautological quotient factor bundle. Okay. And then you see what I can do. I can consider the following bundles. Consider the bundles. Well, S lambda Q tensor SAR. So lambda now is a partition, lambda 1, lambda n minus 1. And A is an integer. So I mean by this of minus A, actually. Okay? And then there's a recipe for cohomology of this bundle, which is like this. So that's kind of a classical theorem from representation. So H star of S lambda Q tensor SAR is determined as follows. What I do, I look at the sequence lambda A, which is lambda 1, lambda n minus 1 A, and I do the following things. First, I add my element rho. Rho is n minus 1, n minus 2, 1, 0. So I look at lambda A plus rho, and this will be lambda 1 plus n minus 1, lambda n minus 1 plus 1 A. This is a sequence of integers, okay? And now I have two cases. First of all, it could happen that in this sequence I have a repetition, okay? If lambda 1 plus n minus 1, lambda 1 plus 1, lambda n minus 1 plus 1, A has a repetition, which means that A is one of those numbers, because you see these are decreasing. The partition was, this is a partition, so since I added this, I have bigger here, okay? So this can happen only when A is set. But if this has repetition, then all cohomology of my bundle is 0. No. Now, if not, if lambda A plus rho has no repetition, then, so these are different integers, then of course I can permute them in such a way that they will be decreasing, okay? So there exists unique permutation in Sn such that W of lambda A plus rho is decreasing. Okay? Now, and if it's decreasing, then I can subtract rho from it and I'll still get a non-increasing sequence, right? So I define mu to be W lambda A plus rho minus rho. And this is non-increasing, non-increasing. Well, it satisfies this, right? Yeah, non-increasing. So then, in such a case, in case 2, there's only one cohomology. In case 2, the only non-vanishing cohomology is the one with a number which is the length of this permutation, number of inversions, of this S lambda Q tensor SA R, and this is S mu on E. The Schur factor on this partition mu. If you get negative numbers, you have to adjust by the power of determinant. But you see, so notice what this means. It means, first of all, that all those bundles satisfy the first condition, that for every j, because what does it mean that I twist by j? I twist by j by changing this number a. Okay, I keep lambda the same, but I start changing this number a. And the point is, for each such twist, I have at most one non-zero cohomology. Okay, but moreover, for which values of a I will get a root, I will get 0. Exactly, you see, for those values of a that will be equal to those numbers in this sequence when I add it. Okay, but a really means twisted by minus a, so this means that this bundle will have the roots of Hilbert polynomial R minus lambda n minus 1 minus 1 up to minus lambda 1 minus n plus 1. Okay? But of course, so they come out negative, but I can move up and down by just doing a general twist j. So it doesn't matter. So in this way, you see again, choosing my partition, I can get arbitrary differences, so I can get arbitrary root sequences. So again, the supernatural vector bundles exist, okay? And so they prove that the cone exactly look like this cone of Betti tables. So now, well, the thing that they did also, which is the key, is to define the pairing. Because you see what really happens is this thing. I have those two cones, okay? So that's right. So they excuse me?
We cannot find high homology
L of W. That's the length of permutation W. You have a permutation W that makes this sequence decreasing, which really is very simple, puts A in the proper place, okay? So it's very, but so length of this W, number of, so basically how many terms you went through, that's your I. That is non-zero, okay? So you see, I have those two cones, the Boij-Soderberg cone and the cohomology tables cone. And what happens, so they define a pairing, which I kind of say something about in a moment. And what happens like this, every extreme array of this cone will define the facet for that cone, and vice versa. Every extreme array for this cone will define the facet for that cone. Okay? So that's the picture that one gets. Okay? The point is, one needs to define this pairing, and here the things get a little complicated. So I just write out kind of the first approximation pairing, and then kind of the equation for the actual pairing, but will not say much more. So pairing between CT cone and Boij-Soderberg cone. So first of all, if I have a vector bundle E, then there exists D0 such that for every D bigger or equals than D0, HI E of D is 0 for I bigger than 0, right? That's their theorem. So I take to this, I associate the module N of E, which is summation D bigger or equals than D0, H0 Pn minus 1 E of D. And this is sim E module. Right? Kx1 xn module. Okay, and then this module I can replace by its free resolution. Okay. So really, they construct a pairing between between two free complexes, okay? And the first pairing, so first pairing is basically like this. Let me just write summation. So this came from the cohomology table gamma ij. This came from the Betty table beta ij. Okay. So first they define sum over all ijk, j smaller or equals than I, minus 1 to I minus j, and here you put beta ik gamma j minus k. So this this you can understand as basically summation over j and z, Euler characteristic of f bigger or equals than j, tensor hj of E. And this argument in the paper, if you look in the paper, it's not too complicated. You basically look at the tensor product of those sequences, and you look at the spectral sequence, and you see this is kind of like the zero part of the Euler characteristic. So this you can see in the spectral sequence if you actually, that actually it's a dimension of one vector space. It occurs, you know, it's a spectral sequence of a double complex, and you can see that it really comes from one vector space, so it's non-negative. So that's right. So that's the point. There's a first theorem that they prove that this is always non-negative. So this means theorem Eisenbach-Schreier, that if if beta ij is a Betty table of a resolution, free resolution, and that's the point, not necessarily minimal even, gamma ij cohomology table, then this beta ij gamma ij defined like that is bigger or equal than 0. But that's the point. You see, this is in a sense too good because it works for every free resolution, not necessarily for a minimal free resolution, but the cone of Betty tables of all resolutions is very different than the cone. So then, what they did, well, by experimentation and by writing the facet equations explicitly, they found those improved functionals. So Eisenbach and Schreier improve beta gamma to the following functionals. I just write a formula. It's beta gamma but really I don't have too much of an understanding of exactly why this comes up that way. But they define those beta, gamma, c tau, where c tau are integers. And this is summation ijk, j smaller or equals than I. And now here you have condition either j is smaller than tau or j is smaller or equal than I minus 2. And here you have the same thing as before. Beta ik gamma j minus k. And now they have the correction term plus summation. So they basically notice that that's what one has to do. K epsilon 0 smaller or equals than epsilon smaller or equals than 1, k smaller or equals than c plus epsilon, minus 1 epsilon beta tau plus epsilon k gamma tau comma minus k. And then they prove the main statement is that these are the right facet equations, and so theorem Eisenberg-Schreier is that beta, gamma, tau c are bigger or equal than 0 for all Betty diagrams of minimal resolutions all c tau and all gamma from homology tables. So these are beta, gamma, c tau turn out to be the correct facet equations. And the way they got it is first they wrote down facet equations for small cases like P2, and actually the key was that for one of them they recognized that this is homology table of the tangent bundle on P2. So this gave them really the hint, okay, but of what's going on. Well, so then one gets the final theorem, Eisenberg-Schreier, then a Betty table, beta is a scaled and up to scalar Betty table of a Cohen-Macaulay module if and only if beta is a non-negative sum of pure diagrams, and then in this case those diagrams can be taken from one maximal chain. Okay, so that's the situation. And so of course it seems like this is just the beginning of some story. Yeah, a question? Yeah.
Sorry, what do you mean if there is from 0 to 1?
Well, it could be either 0 or 1.
Yeah, epsilon there is.
Yeah, either 0 or 1. So you just have either beta tau k or beta tau plus 1k. It's an integer, but it's okay. So you just, yeah, you have like this, and then you have kind of the neighboring ones, something from all degree 1 stuff, yeah. Okay, so yeah, so you could write here epsilon in 0, 1. If you want. Yes.
There was multiple signature, and this theorem is the key.
That's right. That's right, because now, that's right, so one of the applications that was, but you see the point is historically already Boij and Soderberg making the conjectures, they already wrote down on one page how multiplicity conjecture would follow from this. That's why multiplicity conjecture follows almost immediately, because the point is that the product of those di's is an increasing function of the, if you take pure resolutions and the degree start increasing, this of course will be increasing function. So if something is in the cone, then it's trapped between the product for, you know, at least between products for two pure resolutions, so it really reduces to pure resolutions, where it just again gives you Hertzog-Kuhl equations. Okay, so this also shows how you should use this, you know, this technique. Okay, so let me talk about some open problems which I think are interesting, and because now it seems like a lot of people start working, you know, on how to develop in different directions, and there seem to be nice perspectives. So yeah, so first, what is the lowest multiple of primitive integer vector on an extremal array that corresponds to a module? Okay, so here there's a conjecture from this EFW paper that so if D, if maybe, well, yeah, if beta is a primitive integral vector on an extremal array, then there exists n in n so that for every n bigger than n beta corresponds to a module. So for this, it's enough to basically populate with modules enough of the multiples of beta, so GCD will be 1. Of the multiples will be 1. And I remember we run a check for n equals 3, and you know, all ei's smaller or equals than 5. And then we looked at the three constructions of pure resolutions that exist now. Okay, so there's those two constructions from this EFW, and then the construction of Eisenbahn and Schreier that actually works in every characteristic. And then more or less in half of the cases from those three constructions we could get GCD equal to 1. Okay, roughly. But there were a lot of cases that GCD equals 1 was not achieved. So even for n equals 3, you know, would be interesting to actually produce enough of those pure resolutions to have GCD equal 1. So that I think is kind of the easiest problem that probably one could think about. That's right. Then second, do decompositions of Betti tables have a meaning in terms of deformations? Deformations of modules. So you know, this is really related to Hilbert schemes. One could hope, but it seems very far off at the moment, that if you have a Betti table, you know, of some module, then you can move it on the Hilbert scheme to a direct sum of the modules, for example, with the corresponding pure resolutions, right? At least a big multiple, a big direct sum of that module, so everything becomes integral, right? So that's right. Your Betti table is a rational combination, so you multiply by big enough integers, so it will be an integral combination, and then you might hope, you know. But I remember I took part in some workshop where people were speculating on that, but it seemed to be still very far. Now, an interesting problem, what are the extremal rays of cone of Betti tables when kx1xn is graded in a non-standard way. Okay, if you put the degrees of the variables to be, say, positive integers. So this, I think, are somehow the problems about the Betti tables. That, yeah, I would like also maybe to put out something which is kind of, from my point of view, as this equivariant Boij-Soderberg. So basically I have this A equals sim V, sim E, and suppose I take a GLE equivariant resolution, minimal resolution. Can it be up to filtration written, or maybe when you tensor it with a representation, can you then filter it by those pure resolutions that were equivariant? Okay, so the same problem in the equivariant setting. Okay, for equivariant, for GL equivariant, GLE equivariant, complex F, can we filter F tensor some representation, V representation of GLE, so associated, so factors are pure equivariant. And then there are, I think, another perspective that the whole thing opens is analyzing the cohomology tables. Yeah.
Your first conjectures, does n depends on specific?
Yes, n depends on beta, depends on extremal ray. Okay. Yeah. So when you have an extremal ray, here's your vector. Right, primitive vector. Does there exist such things that everything after it can be populated by a module? Okay, so even this is not known, even for an extremal ray, even for n equals 3. Okay, I'm not sure even if it's known for n equals 2, but somehow n equals 2 is always like easy, so probably it might be. Okay, so that's. But now, so there are many questions about cohomology tables. So you see, now we can define if X in Pn is projective variety. We can talk about the cone of cohomology tables of, say, vector bundles on X, or even coherent sheaves. Cohomology tables of vector bundles on X. So the questions are, what are extremal rays? Okay. And then this is related to so-called existence of so-called Ulrich sheaves. So one knows the answer basically by projection formula. So let me just do this definition. Say, well, let's have a sheaf F on X is an Ulrich sheaf if, and maybe dimension of X is D here, First, for every j, there exists at most one I such that HIXFJ is non-zero, the natural homology thing. And second, the Hilbert polynomial chi, Hilbert polynomial h of f has roots -1, -2 up to -d. So really it behaves as exactly as a sheaf O of 1 on Pn. Okay? So behavior S of 1 on Pn. And then there's a simple projection formula argument that if this is true, if X has an Ulrich sheaf, then the cone looks the same as on the projective space, okay? So if X has an Ulrich sheaf, then CTX is CT of Pn. Okay. And then there's no known example of X in Pn, projective variety, with no Ulrich sheaf. But I don't think it was explored. So I was trying with this, a graduate student, Stephen Sam, who was a graduate student from MIT, to investigate this. So we could find Ulrich sheaves on Grassmannians. It's easy to find Ulrich sheaves on all Grassmannians, for example. But already on a three-dimensional flag variety, okay, we could not find an Ulrich sheaf. So it's because from my point of view, I mean, homogeneous spaces are especially interesting for that. So so does there exist? There exists, say, Ulrich sheaf on a homogeneous space G mod P. G is some reductive group, P is a parabolic. So yes, for Grassmannians, and we already don't know for G mod B where G is SL3. Okay. So here certainly there's no line bundle that is an Ulrich sheaf, okay. But we don't even know whether there's an equivariant vector bundle that's an Ulrich sheaf. So this seems to be actually complicated, but maybe not. I mean, because we really don't have at that point that much experience with this. So there are techniques. So these are, and I know there are papers, maybe by Hartron and some collaborators, about existence of the Ulrich sheaves maybe on curves in P3 or something like that. They were recently on the archive. Okay, so if you just Google Ulrich sheaves or whatever, you should be able to. So these are, I think, the interesting problems, and there's also multigraded case, toric varieties. So again, a multigraded case when you have, say, Z2 grading on your KX1XN. What are the extremal rays in the cone? Okay, so maybe I write here number 5, multigraded case. I think a lot of people seem to be working on this. Okay, so I think that's everything that I have to say, and questions, yeah.